Are we recording now? All right, we're recording now. All right. I'll just cut out your embarrassing destruction of the whole thing. All right. Okay, here we go. 2.7, friction on an incline. So we are going to take what we did last week with friction, and we're simply going to add the complication of angles. Okay? And in this case, we're going to use our shoe, and we're going to use a ramp, and we're going to figure out friction on an incline. So you guys can see the shoe up front on the ramp. Everybody can see that? Everybody at home can see that as well. Is there friction? Is there a friction force on the shoe right now? Boys, lock in. Is there a friction force on that shoe right now, sitting on the table like it sits right there? No. Why not? It's not moving. Hold on. Let's back up a second. Does the fact that it's not moving, is that what tells you there's no friction? No. Could there be friction on an object that is not moving? Yes. So... yeah, there's nothing trying to move the shoe. And I know that seems like just a play on words, but right now there is no friction on the shoe. What is the definition of friction? A force that, one more time, opposes motion. So you're right. If there's nothing trying to move, there's nothing for friction to oppose. As soon as I do this, now is there friction? Yeah, because I'm trying to push this shoe. All of a sudden, friction would spawn into existence. Okay. No friction, we agree? How about now? Well, it's the same shoe. It's still not moving. Why is there now friction? Well, yeah, it's on an incline. You're close. That's kind of, you're using the right terms.
Like the forces aren't balanced because gravity and the normal force aren't like head on anymore. There's no acceleration though, so there still should be feeling.
It should be going down, but it's not because
What do you mean it should be going down?
it should be going down because you turned it this way, and so there's more of it coming.
So if this was not a wood ramp, if this was ice, what would the shoe be doing right now? It would be sliding down. So just like when we started and I tried to push the shoe and it wouldn't push, now there's all of a sudden friction because it's opposing the motion of me just pushing it with my finger, right? This is technically the same, right? Gravity is kind of trying to push this thing down the ramp. And again, if this were ice or if this was like the surface of an air hockey table or something, would the shoe move? Yes, probably. Why does it not here? Okay, yeah, because of the surfaces that are in contact, right? So again, this is where we go back to the definition of friction, how it works, how it's defined. It's going to stop this shoe from moving. And again, if we continue to raise this ramp, eventually, at some point, what do we predict is going to happen? Shoe will slide down. How high? At some point. Hopefully. What if I glued it to this? It's all a trick. Oh. Okay, so at some point, at some angle, what happens? It moves. So what's happening with our forces at that spot? Unbalanced? Okay. What kind of friction is this? I think you just said it. Is this, what kind of friction is this? Static friction. How can you tell? It's not moving. Right? And then as soon as that breaks loose, then what happens to our shoe? Starts to slide down. The forces become unbalanced. Eventually, hopefully, allegedly. Here we go. Everybody see that motion? There it is. All right. All right, so that's all well and good. Let's draw our free body diagram here. What forces are we going to label on our free body diagram? Gravity. What direction is gravity? Straight down. Just like we've always drawn it on every free body diagram ever in the history of gravity. We need a normal force on here. I agree 100%. But what direction is the normal force going to be? Perpendicular to the surface. And why? Well, that's how it works. That's literally the definition of the normal force. Right? Because even with this ramp, right, our ramp is still pushing up. If the ramp despawned all of a sudden, what would happen to the shoe? It would fall. So this is definitely pushing up on the shoe. But in this case, by definition, that push up is not opposite the force of gravity, like it has been in every other problem we've done. Every book we pushed across the table, every shoe we drug across the floor, or the sandpaper, or whatever. Right? This now is a little bit different because we have a ramp. So in this case, our normal force is perpendicular to that ramp. What other force must we have? Yes, sir.
Force of friction.
The force of friction. How do you know? Yeah, because otherwise it would move. So I want to draw, well, let's say, what direction do we draw this arrow? Back? Parallel. Why parallel? Because it opposes motion, but it's kind of interesting to say here, what would the motion be if this were to move? What direction would it move? Down the ramp, right? So I'm not going to draw this motion on my free body diagram because on the free body diagram, all we want to see is forces. One day, I record a video, and somebody comes in here wearing 400 little bells. That's just how science works sometime, you know?
It's called
Holiday cheer. Holiday cheer. You got me. All right, so the motion would go this way. So what direction does that mean the friction will be? The opposite. Force of friction. So we've got some forces on here. What was the motion of our shoe? Hold on. Let's get a prop in here. All right. What's the motion of our shoe right now?
Nothing. Nowhere.
Is the shoe moving? No. So what then must be true about our total net forces on the shoe? They must all be balanced. And so this is kind of the key. As I have this drawn, do those look balanced? Now I just drew it, so you guys know how legendary my drawings are. Well, if we change the angle, the friction force will change, right?
But also the motion force or the opposition force will change.
All of the above, right? As soon as we change the angle here, a lot of things are going to change. But ultimately, our free body diagram, as we've drawn it here, is going to kind of look the same, right? But since there's no motion, there's no acceleration, more specifically, all these forces must be balanced. So in that case, there must be some kind of force this way, right? To balance the normal force. There must also be what? Some kind of force this way that balances the friction. Sort of. All right, so you're getting to it. Yes. Okay, so hang on to the trig. We're going to get to that. When we were playing catch with a ball, when we were doing projectile motion several weeks ago, what did we have to do to that motion? That initial, at some angle, toss or throw or kick of a ball, what did we have to do with that initial vector, that initial trajectory of the ball in order to solve a projectile motion question? Yes, so you needed a vertical component and you needed a horizontal component, right? Because ultimately that's all projectile motion was. It was something going outward and something going upward or downward or whatever. How is this the same but different? Kind of. Because yes, you're right, but what's the difference here? Well, what direction is gravity always going to be? Always straight down. So regardless of whatever's happening here on Earth, you're always going to have that one vector straight down when we're talking about forces. But since we're on an angle, and think of the definition of the normal force. Think of what we're talking about with the friction force. What will generally be true about the friction force and the normal force of an object on a surface? Think about their directions. Yeah, they're going to be perpendicular to each other, right? Because the normal force is perpendicular to the surface. The friction force is going to oppose the motion of that surface sliding one way or the other. So this is going to be the same but different. But we're going to have a 90-degree angle in there. Bro. So if this is our drawing, let's explode out this force of gravity is going straight down. But to your point, we need kind of the down the slope part of this, and we need the perpendicular to the surface part of this. And the way we kind of have that drawn, the normal force kind of comes up like this, right? Boy, that's terrible. That's not even close to how I drew it. There's probably a tool. Oh, come on. There's probably a tool to be able to draw dashed lines. Is that closer? It's terrible. We're going to make it work, though. So there must be, if there's a normal force perpendicular to this surface, there must be a portion of the gravity perpendicular to that surface, right? If the surface is pushing up, right, keeping this shoe from floating off into space, there must be a portion of the gravity holding it down. Is this portion of the gravity going to be more or less than the total of gravity? Less, right? Because we're only talking about the slice of that gravity that's diagonal. We also talked about there was the force of friction here. So what must be opposing that friction force? Well, what gravity is a force, right? So gravity is doing what to the shoe? Pulling the shoe. And in what direction can the shoe move, right? What motion? So there must be an amount of gravity here pulling. I know. I know. I wasn't exactly sure I started with the G, and I knew it needed to be a pull. We got there. So I'm going to translate this thing here, this vector, down to here. And I'm going to just fill this in. And what have we created? A right triangle. So what tool can we get out of our toolkit? SOHCAHTOA. That's a great question. What did we say about the sum total of the forces? The forces net on our shoe are equal, are going to be balanced. So, to answer your question, what is going to be true about this and this? They're going to be equal. What is going to be true about this and this? Ask your question.
Force of gravity and you have the force of gravity. Are they the same?
So the force of gravity is pulling straight down, right? So similar to a projectile motion question. When I threw the ball, some of that was outward and some of that was upward, right? Projectile motion. This is kind of the opposite. All of the gravity is pulling straight down, right? The force of gravity is straight down. But if you have something on an angle, well, some of that gravity is going this way and some of that gravity is going down the ramp. So in this case, like projectile motion, we want to break that force of gravity into the two perpendicular pieces that we care about. Because this, while useful, will not get us to something like the coefficient of friction. What do we need for the coefficient of friction? Yeah, so we need this and we need this. But right now, all we have is the force of gravity, and we have some angle here. We'll call it 14 degrees. So let's blow up our triangle here. Boy, this is what you're going to get. So does anybody remember the mass of our shoe from the other day?
2.8. Or no, 3.
3 newtons. So that would be the weight of our shoe. The mass of the shoe would be that divided by 9.8, whatever. Okay, so we're going to call the force of gravity 3 newtons. Right, that's the mass of our shoe times 9.8. You guys calculated this last week when we did the lab, right? Remember? You guys weighed the shoe, you had the little scale doohickeys? No memory? Anybody remember that?
I do.
You need me to drag a spring scale out?
No.
You could weigh the shoe? Okay.
Carl doesn't remember because he didn't do any of it.
Of course not. It's ridiculous. All right, next, we have to decide. So we have our triangle. This, the hypotenuse, was the weight of our object in newtons. Where does the 14 degrees go? True, but we've got 2 other angles here. We've got this angle and this angle. The 14 degree has to go somewhere.
The top one. The top one. This is the top one.
Why the top?
It's directly opposite of the one on the. That's down there, and that's like geometry rules.
Yeah, so 14 would be like, if you made like a
It's like the opposite thing. The opposite.
It's just physics, boys. There's no need to fight over answering questions. We can get there. Here's how I think of this. You're right, it's going to be this angle up here. Because as you lift up a ramp, right, as we go from 0 to slowly lifting this, this is the side that will start pulling away. Now, if you want, we can get into geometry and draw this all out and do complementary angles and all that kind of stuff. We can do that if you're really feeling froggy. Or we can trust. Let's trust. Let's go with trust. So this angle is 14. Can we find this and this? So Katoa, ready, set, go. Yeah, don't trust the scale of my drawings, bro. That is a recipe for disaster. All right, did we get some numbers here? All right, let's start with the perpendicular gravity force. Let's start with the adjacent. Okay, and what's our other one?
0.72.
So let's start with a somehow appropriate smell test of sorts here. Do these numbers make sense?
Yeah.
Right? If our angle is just 14 degrees, should there just be a smaller force pushing this down the ramp, or I guess pulling this down the ramp? Should this number be smaller? Yeah, I can agree with this. And then what do we know about these forces as they relate to our friction and our normal force? Which one is this? This was our force of gravity perpendicular to our surface, so that also equals what? Our normal force. This one was our force of gravity pulling down, maybe the longest subscript notation for a variable of all time. You guys have seen it here first. You were witness to this. We have set a new record in the field of math and physics. Go ahead.
Can you put just FG pull, or do you have to write down? What way to pull it? Could be in a square thing.
I mean, yeah, be specific. Let's just trim this to what is this equal to regardless? Okay, so totally different question, but we can handle that next. So you're right, at this point it's not moving, so these are balanced. If they were unbalanced, what would happen to all this stuff? For example, did you go sledding last week? We had all the snow.
No.
Bro.
I went drifting, but.
Okay, it's totally different and sounds twice as dangerous. Let's play make-believe. Have you ever gone sledding?
No.
Yes! Please! Okay, what's your velocity at the top of the hill? What happens as you slide down the hill to your velocity? Faster and faster. So if you're going down a hill on ice, snow, whatever, unbalanced forces, right? And your speed accelerates as you go down the hill. I'm going to hold on to the shoe this time. Do you think when I let go of this shoe, the forces will be balanced?
Yes, I do.
Maybe. If they're not, what's going to happen to our shoe? It's going to accelerate down the hill. So, spoiler alert, I'm going to utilize that later this week, going up to and into maybe say a quiz on Friday, where they won't necessarily be balanced. So I wasn't going to do that, but since Olivia asked, maybe we should go there. Yeah, I know, it sucks. All right, so let's do one last thing. At 14 degrees, what is the coefficient of friction? For our shoe and our ramp, can we calculate this? Given what we just calculated, can we find mu? Maybe. Theoretically, indeed. So this equals f of f divided by f of n equals 0.72 divided by 1. I don't have a calculator. Somebody help. Help! We'll just call it 8 in between. One of you is probably right. I don't know that we need this answer to the nearest thousandth anyway, but so do you see what we did here? What will happen if we increase the angle? Everything changes. Will this be the same?
No.
Will the coefficient of friction remain the same?
No.
Why not?
Because maybe it will change proportionally. They might be changing proportionally. No, it's not like my logbook that card threw on the ground. It's right so no, it's not.
What will the angle change?
The force of friction. They'll change everything, but it's changing.
Yeah, so it's going to change some things. Will they necessarily change proportionally? I don't know. Let's do the math. Oh my goodness. So let's do our ramp here. But this time, let's go to, I don't know, 38 degrees. Same shoe. Same shoe, same mass, different angle, but we're going to say at 38 degrees, our shoe is still not moving. So look, bro. I obviously drew that way higher than 38 degrees. But that doesn't matter because your calculator doesn't know how terrible an artist I am. So calculate the new coefficient of friction for that same shoe. We're going to assume it's not moving and the angle is 38 degrees this time. All the same forces, everything balanced. Let's say the shoe is not moving, but let's see if our coefficient of friction changes. We're going to say balance. We're going to say the shoe is not moving. We're going to say the shoe will still stick at 38 degrees. Rerun your triangle and rerun the math and see if the coefficient of friction stays the same.
Is it still 3 newtons?
Yeah, well, same shoe, same weight of the shoe, 3 Newton shoe. Different number then, huh? I don't know. We'll see. We'll wait and see if Team Sweaty Physics gets the same number. I love to hear a passionate discussion about significant figures. I love to hear it. I love to hear it. I love to hear it.
Yes, and it's always freaking way for me. Even though I never get it wrong. I never actually mess it up. Because you at least get the math wrong and they're doing work.
I think I got it wrong.
You just don't really do anything. You're just happy to work. That's kind of it.
I think I did something wrong here.
By copying it down.
I agree. These numbers seem too close, and you've also got this angle. Remember, that angle should be at the top.
Oh my.
So make sure you draw that triangle right. No. I think you've got them. Yeah, I think you've got them upside down, and you've got your triangle. This is fine. Well, remember this one here is the friction force. This one, you've got these, I think, upside down.
Was it flipped from the other triangle?
Mm-hmm.
It is?
All right, because if you draw it, you kind of twisted your triangle a bit, right? Because this, if you turn your triangle, this is the one going up the ramp. That's the
Oh, 'cause
friction
you
one.
flipped it, 'cause this
Yes,
one you had the-
yes, yes. So again, you need to be careful with your drawing here on which one is the normal force and which one is the friction force. Yes.
The adjacent and the, like it's the same thing, it's just flipped, so it's like.
Now, the way you draw your triangle is important. And once you solve this triangle, I try to keep it this way, so I always am keeping that force of gravity straight down. And then the other things relate to how my ramp looked. But I've seen some of you are drawing your triangle like this, which again is fine, but you've got to keep straight what's what. And which one of these things is the normal force, which one is the friction force. You've got to be careful on how you kind of label your triangle. What do you come up with for your coefficient? 0.78. So definitely not the same. Let's keep going. What will happen? I did do 784. Obviously. What happens if we double the mass of the shoe? What is your guess on the impact to this number? I mean, it's going to do one of three things. It's either going to increase or decrease or stay the same.
Wow, good one. Climb to that answer the question.
I'm here to help. I'm here to help. Try it. Change this. Change that to 6. Same everything else. Same angle. Same, it's not moving. Use the 38 is fine. I'll get out the tape. We'll tape these shoes together if I have to. But what will happen if we just double the mass? So the weight is going to double. If that 3 goes to 6, what do you predict is going to happen to our coefficient of friction?
Because that angle does not look like 38 degrees to me.
I know, my drawing skills. I don't have another stack of logbooks, or we could move it up to 38 degrees. I could use those. Or, and hear me out, we could just use your imagination that the angle is higher. Just use your imagination.
In the first round.
1.14, 2.38. I mean, that looks. What was the actual number? 1.42 or something? What do we have in our first example? What was it? 0.24, 0.7. These numbers. These don't look right. Oh, at 38 it does. But the first example we had was. Yeah, you had it right here. So this is right. So this is the second. That doesn't look right. Try sine 38
3.69 divided by 4.7
times 3.
equals 0.781286.
1.8. You had 1.14. So that's where.
Wow, you're so
All right, what do we find out? It was the same. It shouldn't. If it went down a little bit, that's just your rounding. If you calculate this with no actual numbers, you're going to get the exact same answer. It's going to end up being sine 38x over cosine 38x divided out. You're going to get the same number.
That's really creative, though.
If the weight changes at all.
Yeah, does the mass of the thing matter?
No.
What matters?
Angle.
Okay, the angle, and what else matters then?
The surface.
Yeah, the actual surfaces are what actually matters, right? This particular shoe and this particular wood plank, if this was ice, it would be different. If this was an air hockey table, it would be different, so on and so forth, right? If this was you sledding down a hill, different surfaces, yes.
These equations are only for static friction, right?
Sort of.
Then what have you done?
What have you done? Oh my gosh. So in this case, the answer is sort of. So if this is our static coefficient of friction, at the same angle, would you guess the sliding coefficient of friction is greater than or less than that? Would be lower, right? So if we had this shoe where it's sticking and I started it, it would then continue if I found that perfect angle. Okay, so here we go. If I get it started, okay, so let's keep trying this. Let's start it. Now it goes. So again, your static, it's going to sit here. Once you get it to where it's going to start rolling, then it's probably going to keep rolling and in fact accelerate as it goes down the thing. Obviously not perfect surfaces here. This is a golf cleat, actually. So again, the mass doesn't really matter here. It cancels out, assuming the surfaces were right and consistent and smooth and whatever else. Tomorrow we'll do some bell work. We're actually going to do this experimentally tomorrow too. Olivia, you want to do the thing?